Welcome everyone to our second video on acid-base neutralization reactions. And in this video, we are going to use a different method, which actually is a faster method to solve acid-base neutralization reactions. Before you watch this video, I think it's important to watch the first video where I go through the regular stoichiometry method, so you have that fresh in your mind as we go through this problem here. Now, this video is going to be longer than the last one, but you'll see when you solve these problems that this method is actually faster. But I'm going to go through the reasoning, the background behind it as we go through this problem. So it's the same question as we solved in the previous video, but let's once again start off with a balanced chemical equation. Now we're going to make use of a skill that we've learned this year, and that is writing net ionic equations. So for this equation here, before we solve it, let's write out the net ionic equation for this problem. So take a moment, pause the video, try this yourself. It's great practice to see if you remember how to do this. Okay, so here is the total ionic equation. Recall that at this point here, we are going to cross out the spectator ions, ions that appear in the same quantity, charge, and state on the reactant side and product side. In this case, the sulfate and the sodium ions are the net ion or are the spectator ions. And so my in 3, 2. So here's my total ionic equation. And recall that the next step is to cross out the spectator ions, ions that appear in the same quantity, charge, and state on the reactant side and the product side. And in this case, our spectators are the sodium and sulfate ions. And so my net ionic equation is as follows. 2 hydroxide ions reacting with 2 hydrogen ions to produce 2 water molecules. Recall that a net ionic equation is showing us the actual change that's occurring. So in every neutralization reaction, the chemical change which is occurring is that equal quantities of hydroxide and hydrogen ions combine to form water molecules. So if you take any acid-base neutralization reaction, you balance it, and then you get down to the net ionic equation, even though the coefficients will be different, the overall structure will be the same. Equal moles of hydrogen and hydroxide ions reacting to form water. Because at the core of every neutralization reaction, equal quantities of hydrogen and hydroxide are combining, we can take advantage of that and develop an equation that is going to simplify the process of solving these problems. I've rewritten what I just said in the form of an equivalence. When an acid has neutralized a base, the moles of hydrogen ions will always equal the moles of hydroxide ions. So this is going to be our starting point. My next step is to convert this into quantities that we can actually measure, that are often the quantities that are given in the problems that we want to solve. My next step is going to be making use of the moles is equal to molarity times volume equation. Moles of hydrogen ions is equal to the concentration of hydrogen ions multiplied by the volume that the hydrogen ions are in. Same with the other side. Now, we can simplify this equation again because the volume that the hydrogen ions are in are just going to be the volume of the acid, because remember, the volume is really the volume of the solute. So it doesn't matter what species we're talking about. That's just the volume that we're dealing with here. So since the hydrogen ions come from the acid, the volume of hydrogen ions is equal to the volume of the acid. The volume of hydroxide ions is equal to the base. I'll just use A and B for acid and base. Now, the concentration of hydrogen ions is not always the same as the concentration of the acid. And we've seen that a few times in some problems that we've solved. The concentration of hydrogen ions is going to be dependent on the number of hydrogen ions in the formula of the acid. And this is a great example here. Let's look at this line at the top. We have 1 mole of sulfuric acid. However, since in every 1 mole of sulfuric acid, there are 2 hydrogens, that 1 mole of sulfuric acid actually produces 2 hydrogen ions. So in order to find the concentration of the hydrogen ions, we need to multiply the number of hydrogen ions in the formula of the acid by the concentration of the acid. We'll do the same thing with the other side. The concentration of hydroxide ions is equal to the concentration of the base multiplied by the number of hydroxide ions in the base formula. This line here in purple, this is called the neutralization equation. In order to solve this problem, we need to know the identity or the formula of the acid and the base, because we need to know the number of hydrogen ions and hydroxide ions in those formulas. And as long as we know 3 of the other 4 quantities, we can solve for our unknown. And the unknown in acid-base neutralizations is almost always concentration. We want to know the concentration of an unknown acid or base. This formula is only true at the point of neutralization. It's resting upon the idea that at neutralization, the moles of hydrogen ions is always equal to the moles of hydroxide ions. Now that we've got the background, let's plug in some values and use this equation to solve the problem. The question is asking for us to solve for the concentration of the acid, which is M sub A. So let's rearrange the equation and solve for the concentration or molarity of the acid. The number of hydroxide ions is the number of hydroxides in the formula of the base. Okay, so sodium hydroxide, 1 hydroxide ion. For sulfuric acid, in every 1 sulfuric acid molecule, there are 2 hydrogen ions released. You'll notice that I did not convert my volumes into liters, and this is another advantage of this equation. It's similar to the dilution equation because it's just resting on a ratio, and as long as your volume measurements match, you do not need to convert them into liters. So if they're already in milliliters, just leave them there. So let's plug this into the calculator and solve for the unknown. So we obviously get the same answer to the problem here, 0.03785 moles per liter. And just as with the volumes, whatever concentration unit we have in the equation, that's going to be the concentration unit. And remember, capital M is meaning the same thing as moles per liter. So this equation here is much faster. You're just plugging in the values from the formula. The most common error that students make when they're first working with this is they conflate the two methods. You'll notice that when I solved this problem here using the equation, I never made use of the balanced chemical equation. Okay, so I never started using the mole ratio or anything like that. I'm literally just taking my given values and information about the chemicals and substituting them into a formula. A good exercise would be to look at your solution from the previous method of solving this problem and compare it to the steps here. And what you're going to see is that all of the steps in the stoichiometry problem are just embedded here in this one equation. We did molarity times volume, then we divided by 2, and then we multiplied by, or then we divided by the volume to get a concentration. So the equation just says all the same steps, but all in one equation here. But it's important you don't mix up the two. If you're doing the equation method, just substitute the values into the equation. If you're using the stoichiometry method, don't start trying to bring in this equation at some point because then that's where errors will arise.